Okay, so chapter 4 is cellular respiration, chapter 5 is photosynthesis, and you're going to see from today's notes that these two chapters are very, very, very much interrelated. Okay, so just to start, again, understand all cells need energy. You may say, well, plants, they make sugar. Well, sugar's not usable, so all cells have to have energy. If you don't have energy, you're going to die. And again, it must be in that usable form. It must be in the form of ATP. If it's not an ATP, your cells can't use it. So carbohydrates, again, made in photosynthesis, are not a usable form. We tend to think of carbs, that's providing our energy. Well, it has to be processed in order for our cells to use it. Okay, so bioenergetics is the concept of energy flow. How is the energy flowing? And you notice, you see all the arrows, they're all pointing the same way. Energy is a one-direction flow. Okay, metabolism, one of those words we've talked about off and on for years. We tend to think of metabolism as breaking down our breakfast or breaking down our lunch. Well, it's also building up. So it's building and or breakdown of molecules. And again, photosynthesis builds up molecules in the form of glucose or polysaccharides. Again, polysaccharide being your starches, your glycogen, cellulose, which our body can't use, but which is being made. And then cellular respiration is going to break down those molecules or those polysaccharides into glucose, or from glucose into energy. So again, if you look at these, you'll notice that they are reversed. So we've got energy here, we've got energy here, we've got glucose here, we've got polysaccharides here. So they're just flip-flopped, and that's why these two chapters really go hand in hand. Again, if you look at the equation, and you do need to know these equations. If you know one of them, you're good. Okay, I tend to know photosynthesis first, but if I take 6 carbon dioxide from the atmosphere, I add 6 molecules of water, I throw some energy in there, I'm going to make my lovely little glucose here, C6H12O6, and as a byproduct, I'm going to put oxygen back in the atmosphere. Well, if you come down here, you're going to see it's the exact opposite. Energy, energy. Water, water. CO2, CO2. O2, O2, and glucose. So again, but you do need to know at least one of these equations and understand that the other process is the exact opposite. And again, energy is a key component here because energy has to go into the system in order for it to happen. Okay, a little bit of physics. We've got anabolic reactions. Anabolic reactions require energy. I think when we talked about anions, I said anions remind me of ants. I don't like ants, so they were negative. It also takes energy to get rid of them. Okay, so anabolic reactions require energy. But with that energy, we're going to be building things. We're going to be building molecules or synthesizing. Again, synthesizing is just the fancy name for building. Catabolic, opposite here. Again, this is my cat. He's sitting on my lap. I'm just chilling out. So I'm releasing energy. And we're going to be breaking down molecules or degrading molecules. So I'm going to take something, I'm going to break it. Again, remember when you're talking molecules, anytime you have a bond and you break that bond, you release energy. Okay, more physics. Mr. Hook likes to brag physics is the most important of the sciences. Actually, the hierarchy is math, and then physics, and then chemistry, and then biology down at the bottom. But we all know biology is most important. Okay, again, a couple of terms. You've probably heard of these. Okay, so again, thermodynamics is just the study of energy and how it's transferred. We have open systems and closed systems. And for the most part, all life is an open system. So the energy can be exchanged with its surroundings. We know that if we eat something, we're going to release heat, we're going to be able to do action. Okay, it's like the open pot on the stove. You know, you're boiling that pot of water, that steam is going into the atmosphere. It's not staying in the same place, but it's still around. We can't destroy energy. It's just moved around. Again, all biological systems are going to be an open system. Closed system is going to be the opposite. So the energy is contained within the surroundings. Again, if you have a pot on the lid with the stove, the steam can't escape, it stays right there. And you would think, you know, closed system would be ideal, because if you have a closed system, all the energy is staying contained, which would kind of lead you to perpetual energy. Again, it's ideal, but it's not realistic. There's no such thing as perpetual motion. Be nice if there was, but there isn't yet. Okay, laws of thermodynamics. How many of you know the laws? How many of you at least heard these at one time or other? Maybe? Okay. Okay, first law of thermodynamics. Again, how energy is moving. So the total amount of energy in the universe is constant. The sun, the energy from the sun is coming into our environment, into our biosphere. That energy is causing lots of things to happen, and you may say, well, wait a minute, we don't have energy going back out. Well, we do, kind of. And so again, it's an open system. Things are always rotating. Energy is constant. Again, energy cannot be destroyed or created. It's only changed in form. Again, this is the first law of thermodynamics, or Newton's first law. Newton was the one who came up with these. Which is really amazing what he came up with back in the 1400s or whenever it was. His second law was, when energy is transferred, it increases the entropy, or entropy is a fancy word for disorder. So it increases the disorder of the system. It makes it more chaotic. So again, energy could be transferred to heat. Again, heat's going to dissipate more. It makes it more chaotic, or have more entropy. Okay, again, more physics. Types of energy. And I'm guessing you probably are familiar with this one. We've got kinetic energy. Kinetic energy is the energy of motion. So if you're pedaling that bike and you're moving, you're experiencing or expressing kinetic energy. The other type of energy is potential energy. And it just has a lot of potential. It's not doing anything right now, but it's got potential to do something. So energy due to position. So again, if you're looking at the bike rider here in the hill, we've got kinetic going up here. So we're getting closer to the top. Our kinetic energy decreases because we tend to get slower. Stop at the top. At this point, we have zero kinetic energy, but we have lots of potential. And then we're coming down here. And again, at this point, my kinetic energy is increasing because I'm going faster and faster and faster. And what you'll notice if you're graphing these is they kind of balance each other out. Okay, we also have a thing called activation energy. And it's just like it sounds. It's the energy required to activate a reaction. So it's the amount of energy needed for a reaction to occur. We have exergonic reactions. We have endergonic reaction. Again, we've seen this prefix EX, so we're exiting. So energy is exiting the system, which means it's going to have a negative delta G. Don't worry so much about the delta G in here. That's definitely more of an AP thing. But for those of you who are thinking on down the road, or you're thinking some physics, you definitely need to understand delta G. spontaneous. It does not require energy to go into it once it's started. And that's a key point, once it's started. So if you're looking at the picture here, you can see we're really kind of starting right here. And at this point, we don't need any energy, and energy is going to actually be released. But we've got to get to this point right here, and this is where the activation energy comes in. Again, think of riding a bicycle. You know, those first couple of pedals take a lot of energy, right? And then once you get it going, it goes more quickly, it goes more easily. So that would be like an example of activation energy. Opposite of exergonic is endergonic. So energy has to go into the system, and you're going to have a positive delta G, or energy is absorbed by the reaction. Again, energy is just moving in. This one is not spontaneous because we require energy. And again, to require energy is going to control whether it happens or not. So again, if we're looking at the curve here, we're going to see that it is taking a lot of energy in order to rebuild our potential energy. So again, this is not spontaneous. This takes a lot of energy to get it going. And as you come back down, you're just going to come back down to a neutral point. Enzymes? Ooh, who remembers which macromolecule is enzymes? Got 1 in 25% chance. We got nucleic acids, proteins, carbohydrates, and lipids. Which one's it going to be? If in doubt, have you ever had a question that talks about which macromolecule is doing something? Always guess proteins, because you're going to be right 95% of the time. Okay, so enzymes are a type of protein. And enzymes are going to lower the activation energy required for the reaction to proceed. So again, if you're talking, so here was my original, here's my enzyme in here. Enzyme's not part of the reaction, it just helps the reaction to occur. Again, if you go back to the bicycle analogy, it's like a 10-speed bike. If you lower the gear, it's easier to start pedaling. So lower gears would be equivalent to an enzyme. Okay, we said that the body needed, or cells needed ATP in order to survive. That's the only energy our cells can use. Well, we also have a product here that's called ADP. And ADP is an electron carrier. If you break these words down, ADP stands for adenosine diphosphate. And ATP is adenosine triphosphate. And again, the name kind of gives you a clue that you got one more phosphate group in ATP. So this one's fully charged. This one's not. He's just around to help carry phosphates around in order to make ATP. And again, what you'll see, and again, most things in biology tend to be cyclical. So your ADP can make ATP, ATP is used, it makes it back to ADP, ADP gets reloaded, it gets used, sends it back. So it just keeps going round and round and round. And again, ADP has 3 phosphate groups. ATP has 3 phosphate groups. I read that wrong. So you might want to clarify that ATP has the 3 phosphate groups. That's why it's called triphosphate. And again, ATP, we lose a phosphate group when we take the energy off of it. Makes it ADP, which has the 2 phosphates. And again, when we break that bond, release that phosphate group, we're going to be releasing energy. So again, every time you break a bond, energy is released. And we are going to stop there for today. We will finish these tomorrow. You'll notice that there are study questions posted. Study questions, I think, are due on Wednesday. I think is what it says. It says they're on paper. I do have paper copies here, so I would prefer that you do them on paper.